So today, basically our tutorial number 5. So tutorial number 5. So in this segment, basically what we will see. So in this tutorial segment, basically we will see that a very interesting topic. And after the end of the segment, students should be able to describe, that is, how to plot some parameter versus the VGS of n in LaTeX or overleaf. So basically this is the outline of today's class. So if you recall that in the previous tutorial video, that was tutorial 4, I discussed how to generate .dat file from Cadence. The corresponding data of the .dat file we were plotted with VGS. The x-axis will be VGS of n. N means NMOS. And y-axis will be my parameters. So we know the parameters are lots of parameters. So we consider the x-axis and as VGS, and then we perform the parametric analysis for different channel lengths of this NMOS and try to understand what the graph actually represents. So actually the highlighting point is, and the very, very important point is that we basically do not need the parameter versus VGS of n curves directly. But the cadence will by default generate this curve and give me this curve. So this is a problem. This is a problem, right? So our main target is plotting, and the x-axis will be always game over ID, and the y-axis their parameters. All right, so there are basically parameters. So today, basically, I try to explain there is how we can plot our parameter versus VGS of n, because in the last tutorial, basically we are generating the .dat files, which are actually corresponding the x-axis as a VGS of n. All right, so now let's go to the Cadence environment. So welcome back in Cadence. So let us log in. So today we basically don't run on any terminal, and we will not work in our simulator, that is Cadence. So for this reason I cannot open the terminal. The terminal is closed. So we will go to the computer, file system, and then home, then work. From here our directory is gm override, and inside this directory I was creating a folder that is .dat file. In the last video I was creating the .dat file, so we need to just copy this folder. So after copy the folder, let us, you see that we have 7 .dat files, and each of the .dat files, the x-axis is the VGS and the y-axis is its corresponding parameters or different length, because we was done the parametric analysis. For this region, different length corresponding the variation, it will actually implies this all the datas. Okay, so now let us copy the folder. Just simply copy it, and after doing the copy, we will go to our Windows environment. So we will go to our Windows, so minimize the Linux operating system, and then we paste. So you see here the folder is successfully pasted here. So now inside this folder you can see all the parameters corresponding .dat files. So if we, let's say, turn on a .dat file, for example this one, so we cannot understand what is actually the set of data implies. So it's very critical to understand in the notepad. So for this region I am using here the Microsoft Visual Studio or Visual Studio. By using this we actually open the code. So now it will be easy to understand. So the first column, this column, if you see for this column, the maximum value is start from, sorry, the minimum value is start from 0. The maximum value is 1. So this is actually our gate voltage or our VGS. You recall that we actually sweep our VGS, and our sweeping range is in between 0 to 1 volt. So that's why we will get this type of set of data column. So this is actually my VGS, and all the other columns for different length condition, and this y-axis is actually this holes. This holes means from this side. So these alls are actually your y-axis corresponding value. Your y-axis corresponding value. So if you see here, this is your minimum length, which is 100 nanometer. This is 300 nanometer. This is 500 nanometer. So our sweeping range was 100 nanometer to 2 micrometer, and our step size was 200 nanometer. That means each step will increase. The incremental factor is 200 nanometer. For the reason we at first get 1 nanometer, 100 nanometer, then 300 nanometer, then 500 nanometer, then 700 nanometer, like that. So the minimum length is actually 100 nanometer. So this column is actually for corresponding 100 nanometer lengths. Ft is value in the y-axis and VGS of n in the x-axis. And these all are actually in your y-axis. So what is the maximum value of here length? So if you see here, our maximum length is actually 1.9 micron. So we have minimum is 100 nanometer and maximum is 1.9 micron. So the first row is actually implies that it is actually nothing but each of these columns header. You can rename the column by using your own wish. If you're not interested about that, you can simply do some trick applying here. So what will be the trick? You simply just delete this column, and also delete this elephant. So we need to modify this code, these dat files slightly, and our x-axis is actually VGS of n. So let us write it, and let's rearrange this in this way. So after that we just save the data. So this is actually our conversion. We need to do the same modification in all the parameters dot dat data. So you see here, this is my id over w dot dat files data, which I already rearrange here. So similar manner we will follow, and after that we get our .dat files. So I already have done some modification on those files. So let us select all the things, and then so let me just show you the GM over GDS. So go to the Visual Studio. So you can see that this modification is also here. So you need to consider this modification for this all the dat files. Suppose we on the vdset.dat file. So if you see here, also I am doing the modification here, right? So you need to do these things inside these .dat files. All right. So after you do these things, you are ready to plot your .dat files in Overlap or LaTeX. So for this reason, what you actually do, okay, so you will go to any browser and type here Overlap, and then search. So after that, you get this interface, you click on it, and using your Gmail account, just simply log in this environment, and after that you will create a new project, blank project, and give a name. Suppose I specify this name as tutorial file. Tutorial file. All right. So after that, you will get this type of interface in your LaTeX. Just simply remove the things, and then delete the main.txt file. So this is actually your working window or working space. So now what you will actually do? So you will actually do that, upload your .dat file in this working space. So simply click on the upload. So we are saving it as a folder. So select a folder. We have a folder, and after that we will select our .dat files and upload it. Just simply upload it. All right, so this is your folder that you have. So now let's expand this. So this is our .dat files. So I already performed some plotting like FTA versus VGS of n. So let me just show you these cards. That is how nice and clear curve we can actually can plot in the LaTeX. Just I will show you some samples. So the first one is FTA versus VGS of n. So basically this is our LaTeX code. This code is actually mixed by my honorable professor. He actually provided me this code. So very thanks, and thank you sir for this code. So we need to tweaking some value here. I will show in detail because I will actually modifying some plots. So now roughly you can see the code, and let's recompile how nice the output can actually be possible in LaTeX. So you see here, this curve is the x-axis is actually your VGS of n, and y-axis is actually your FT. So FT means unity gain bandwidth. So you can download the curve as a PDF format. So let me just save the curve in desktop and rename the PDF as, say for example, FT versus VGS of n. And after that, let us open this PDF. So if you see in the presentation mode, then you can try to understand how nice actually possible this curve. Very crystal clear curve. So this is our unity gain bandwidth. In y-axis this is the FT, there is the transient frequency, and x-axis is actually VGS of n. So we can actually also use the legend. So if we use the legend, the corresponding colors length will be show here. So if you use the legend, I already write down here the legend code. Just remove the comment. So just remove the comment. I will explain in detail how to you actually plot your data in actually overlay. But for this time, I basically showing the output of the LaTeX, because what is the why actually you use the LaTeX? So you need to consider some samples figure, then you will actually interested to plot something in LaTeX. So now if we recompile it, You can see that. Let me just download this again and run on it and see the presentation mode. In the presentation mode, so now you can see that the corresponding colors length are actually wrote here in nanometer format. It's very interesting things. And another important thing is that you can use this figure in your journal paper if you are interested for research based publication. You need crystal clear curve. So if you want to plot something with like this type of crystal clear figure, you can use LaTeX, and then you can use your figure in your journal. So this is the one of the first example of our .dat files that we are plotting against VGS. So after that, we have also drawn the GM over ID versus VGS. So let's recompile. So you can see that the GM over GDS is basically our intrinsic gain, right? So the GM over GDS is basically our intrinsic gain, and the x-axis is actually our VGS of n. So you can see that this is the plot, and actually this is your main data. There is no unnecessary data actually. This is your necessary data. So we can observe these things. So if you're interested, you can add here legend, and then the corresponding lens color will be show here. So I also draw here GM over ID versus VGS of n. So let me just recompile this. So now let us download it and open it. So now you will see, you can see that your y-axis is actually GM over ID, and your x-axis is basically VGS of n, and its corresponding curve is look like this. It's very pretty much clear. So if you're interested to add the legend, you may add it. Just simply uncomment your add legend this. So I think everything is actually done. So now recompile this. Okay, fine. So let us download it. So now you can see here your lengths corresponding color are given by the legend. So if you want to use legend, you can use that function. If you're not interested to use the legend, you may omit those things. So finally, I have ID over W versus PGS of n curve. So if I recompile this one, so you can see here, this is your ID by W over VGS curve. And here we have this actual data. So now let me just clarify how to you actually plot this curve. So you have the code, you not modify anything, just modify a crucial thing in these lines. So first of all, you need to declare your x-axis minimum and maximum value. So we know that our minimum value of VGS is actually 0 volt and maximum voltage is 1 volt. So that's why I am using here 0 and as minimum value and at maximum value as 1. Okay, so there is a proof. Also there is a proof. So if we turn on the ID versus VGS, this uh, .dat file, you can see here this is column is actually your VGS of n. Your minimum value is actually 0, right? And your maximum value is basically 1 volt or 1. So that's how we are writing the x-axis as a minimum value is 0 and maximum value is 1. So what about for the y-axis? So in the y-axis we have ID by W. So if you see here, I'm writing here the minimum value is 1 e to the power minus 4 and y maximum is 1 e to the power 3. So why I am writing the y minimum 1 e to the power minus 4. So let's try to explain this in VS Studio. So let me just do like this. So now it will be easy to see. So you see here your these all are actually your y-axis. These also are actually your y-axis corresponding different length you have, and that length corresponding values are given here. So in your y-axis, your minimum value is e to the power minus 5 here, e to the power minus 5 here, and the maximum value is e to the power plus 2 here. For all the values are actually you have same things. For the different length, corresponding length, you have same minimum and maximum value. It is actually not like that. You have for 300 nanometer, you have minimum value is actually 300 nanometer, but your maximum y-axis value is actually, let's say, for example, e to the power 2. But in your 500 nanometer, your minimum value will be e to the power more or less than, let's say, for example, minus 23. And your maximum value will be, let's say, for example, e to the power plus 12. It will not like that. Minimum and maximum value is actually always covered for all those parameters. Like here, it is actually minimum as e to the power minus 5, and here the maximum value is e to the power plus 2. So this will maintain all here. So you see the last row. Here the minimum value is actually indexed at e to the power plus 1. Here also e to the power plus 1. Here also e to the power plus 1. Here also e to the power plus 1. So you can see that the maximum value is indexed at e to the power plus 1. So our finalized maximum value is e to the power minus 2 here. So for this region, we will consider here the maximum value as e to the power 3. 1 into e to the power 3. And what is actually your x tick? X tick actually implies that how do you actually consider your x-axis. Okay. So suppose if you see here, my x-axis is started from 0.2, then 0.4, then 0.6, then 0.8, and then finally 1. So I select my tick as like this: 0.2, 0.4, 0.6, 0.8, and 1. And after that, I am selecting the y-tick from e to the power minus 4 to e to the power 3, but it will increase like in this fashion. First of all, it is e to the power minus 4, then e to the power 1, then e to the power 3. So the y-tick will be maintained these values. You see here, your first value is e to the power minus 4, then e to the power minus 4, it actually means that 10 to the power minus 4. It is 10 to the power 1, this is 10 to the power 3. So if I change here e to the power, suppose 2, and then recompile it, then you can understand the code criteria. So you see here now this is actually your 10 square, but I am interested for my maximum value, which is e to the power 3. So let us write here e to the power 3. So now we can understand this portion of my curve. There is setting the range of your x-axis and your y-axis by based on your .dat file. All right, so you need to use your .dat files, and by using your .dat files, you will fix your x-axis and you will fix your y-axis, minimum and maximum value. And after that, you fixed your tick, and then you will specify your axis. So if you have some writing something in your y-axis and x-axis, you need to use this function. So I am using here y level as a variable, and inside this I actually write here this string. So if I write this string, it will execute like id by w is in the y-axis, and the unit of the id by w also I mentioned here, which is microampere per micrometer. Similarly, I consider here x level. Okay, x level, so which is VGS of n. So after that, the main doing task is here just in this line. So we're using here the add plot function. First of all, we are specify no markers, thick, line width we are considered 2 pt, color we are using here red. From the table, our x-axis is actually VGS of n, and y-axis will be our minimum length or minimum channel length. So we need to consider as our y-axis value for our minimum channel length. So how do we ensure our minimum channel length? You need to go your VS Studio or your DAT file. So you can see that this is your first channel length, which is 100 nanometer. And after that, you have 300 nanometer, then 500 nanometer, then 700 nanometer, like that. So by depending on that, I actually just editing the code. My y-axis length is 300 nano, then 500 nano, then 700 nano, then 900 nano. So suppose you have 10 length, or you have, let's say, 5 length. So you need to consider those individual 5 lengths corresponding plot by using this add plot function. So similarly, we have 1.1 micro or 1100 nanometer. So you need actually different plot. So for this reason, it is easy to understand for different color. So that's why I am using here different color for different channel length. So after you are doing this program, you need to add here your .dat file location. That's very important. So if you do any mistake here, the code will not execute properly. So how do you ensure your .dat file location? So you need to consider your .dat file folder here. Let's expand this. So you can see that inside this folder you have these .dat files. So you need to mention the folder, and inside the folder you have your .dat file. So that location you need to mention first, and then you mention your .dat file name. So here I am using this command here because our folder name is .dat file. So simply we write here .dat file and then use here a backslash, then use your id by w. because we want to plot the ID by W against the VGS. So we are using here the NMOS ID by W .dat files. So everywhere we are using the same .dat files. And after that, if you do these things properly, just recompile. If everything is okay, there is no problem. In that case, you will get your curve. Suppose you want to add a legend at 1300 nanometer. Just simply uncomment this and recompile this. So you can see that the red color is actually your that channel length. For that channel length, you actually get your 1300 nanometer channel length. All right, so now it's time to see do a new plot in practical in this video. Okay, so suppose we want to plot the vdset.dat file. So what we will do, we'll simply copy any text file. For example, we copy the FT versus VGS of an code. Just simply copy this all code folder again and create a new file, not new folder, new file. So create a new file and the file will be text format. You will write here, that is vdset versus PGF of n. So basically this is your new text file. So now you will you will paste your all the codes that you actually copy before, and now it's time to modify the code. So your xmin will be same, but you will change your ymin. So we need to open the vdset versus vgs of n, or the vdset.dat file. So let's open the vdset.dat file. So we have already created this modified this code. So let's open this with Visual Studio Code. So you see here your y-axis minimum value is actually e to the power minus 2, right? E to the power minus 2, and your maximum value is e to the power minus 1. This is your maximum value. So your minimum value is e to the power minus 2 and maximum value is e to the power minus 1. So we will consider a little bit tuning value. Tuning value means that we are consider the y minimum. What is the y minimum? The y minimum is e to the power minus 2. So we consider e to the power minus 4. So y minimum will be e to the power minus 4. And y maximum will be let's say for example e to the power 1. E to the power 1. So x tick is as usual same, but the y tick will be changed. So how do we will change the y tick? The first starting point from e to the power minus 4, then it will go to directly, for example, e to the power 1. All right, e to the power 1. So the VD set is actually in my x-axis. Sorry, the VD set is actually in my y-axis. So in your y-axis is actually your VD set. So how do you actually write the VD set? You can simply copy this line. me copy this line and let's edit this Y level. So let's delete all the things and alter V. So let us write here V reset. So S A T, and the unit is actually volt. And X level, let us remove the gate to source voltage this sentence, and the unit is actually volt. So in this side the tweaking is actually done. Now the important thing is add your .dat file here very carefully. If you make a mistake here, the compilation will be not occur. So that will be a very big problem. So what we can actually now do, we can simply go to the NMOS.dat here, click on it, and then rename, Ctrl A, copy this name, and go back the VDC versus VGS of n .text folder, and then simply delete this, and everywhere you need to paste this name. So after that you actually save your data. So let's alter save. So if everything is fine, then it will compile. So you can see that it will be not recompiled. There is some error. So where is the error? We need to find out our error. So where is the error? Let's try to find out the error. Okay, fine. So here we are using a double curly bracket. So that's making error. So now we recompile it. So we have this is the last one. So now let us recompile this one. So now you can see here, this is your actual data that you actually need here. It's very problematic situation, that is you can actually interpret this card, but whenever you design something, you have some value. Suppose your VD set is actually let me just download it. So suppose your gate voltage is 0.4 and your VD set is actually some value. So it is very hard to finding your actual length from here. It will give a crystal clear plot, right? But you cannot find your exact intercepting point directly from here. So there will be another mechanism we will introduce here by using machine learning and Python programming concept. We can actually find out our exact length, and by doing that Python programming, it will finding very easily the accurate intersecting point that I need for my curve. This is for the plotting purpose, but if you want to find out the value from your cadence, you can also do this. This is a way that you can plot your cadence data very well and crystal clear figure. So this is your VD set versus VGS. So similarly, you need to plot all the parameters like ftgm over id .dat files and then remaining others. So today I basically want to close this tutorial because the tutorial is actually very lengthy. It will take more times to see the viewers. Whenever the viewers will see the videos, it will actually makes many lengthy time. Already it is actually very lengthy. So I want to basically stop this video in this moment. The next class, we will plot the remaining things with a part 2, a little bit shorter video. Okay, so thanks for watching, and with these I conclude this tutorial. Thanks for watching.